And now we'll go back to our lab 6 and inverted pendulum and control system design. If you look to the lab, you go to the point 714, and what Anas was saying about tuning the PID parameter, this is very important. You can go and watch the video a bit, but I'll taking the same structure. If you look to that structure, you have it here exactly. I make it this way. You have theta, which is the inner loop, and this was the theta angle. Theta came from sensor measurement experimentally, subtracted from pi here in this case, or close to pi, 3 point something in radian. This means pi. In this model or in this system, pi, the sensor measuring pi as the vertical direction. So in our model, in this model that we know, we modeled, it's modeled 0 as the vertical position. So that's why I'm putting 0, not pi. Connected output to the PID controller, and the X, which is the position, subtracted by a reference signal. Could be a step, could be sine wave, could be a given position, and the output of it is going to enter a PID controller, and then subtracted and added to the position, to the angle controller, and the output of it is the force applied or the control effort applied to the motor of the inverted pendulum. Okay, so that's the system. I repeated it here. I make it this way, and let's look at it on the Simulink. I modified our Simulink block to have it look the same. So basically, you go to your Simulink block. I just modified it to look the same. Alright, with the difference that this is 0. So this is the inner loop, and this is the outer loop. Okay, so it's not a strange thing what we are doing in our lab 6 here. Basically an inner loop and an outer loop, and this is what? This is a feedback compensation. So I have here a feedback compensation. Imagine I don't have 0. If I don't have this 0, so this is minus, so means I'm doing a feedback compensation. Well, it could be with 0, it could be with 2 degree of freedom PID here. You could have 2 degree of freedom PID controller, in which you have to input somehow like this. So instead of this summation, I can have 2 degree of freedom. So we can try here, instead of this, having 2 degree of freedom PID, as we did in previous session when we put it here, okay, in cascade or nested architecture. So now I'm keeping it same as we did in the lab anyway, and this is still a feedback compensation as well. And in our previous session, we did a PID, we put a PID controller actually, but without the summation. Okay? We take it directly from here to here, and we had here a PD, remember? So we'll basically do the same now. The question is plus minus or minus plus. What should I put? In our previous session was putting minus plus. Well, it's the same, because plus minus or minus plus, like multiplying by minus. So your effort here, like instead of moving forward, maybe you move backward. So at the end, it returns to change the sign of your coefficient, somehow like this. So then it's the same if I take the blue one or the pink one. It's the same. It's not that big difference. You can put minus plus. Then now, what about plus plus or minus minus? Can I put? You can try it and see in simulation if the system will look like stable or not, with any value of PID if you wish, default value, and try and see if it will actually be a stable system or not. Well, so now how to tune them? As we did before, we can follow some requirement, or considering an inner loop and outer loop. So now I will be considering inner loop and outer loop. So let me close the loop here, and then my system looks like this, and we try to tune that PID. Okay, that's the inner loop. Okay, that's how it looks like in time domain. I can go and find it in frequency 90, 80. Well, I can keep it this way, so it seems fine. Okay, blocker updated PID. Then, alright, now I connect it together and try to tune this one. Also, it seems fine. You can keep it 0.8, or you can, that's the auto-tuned one. I can, let's see the response. Look how. See the response. It seems like your response is not as good. Even so, it doesn't really fail down, but is not as good as it should be. Of course, we know that having state space controller, it gives us really better response, especially in tracking, if you remember the last session. But let me stop it and have different tuning here. Basically, what I want to do is to minimize that thing here. So let's go to frequency, bandwidth. So bandwidth looks high compared to the stable. So now make it smaller in a way to improve the stability. Okay. So let's see if this sounds fine, like 100 times faster, slow. Okay. Did I update my block? I don't remember if I update my block. Let's check. The tuned response, the block response, current block response is this one, tuned response. Well, I maybe it's 0.79 or something, 0.78. Let's see. Yeah, that's the one that I should have. Updated one. Then let's check now if the response looks better. It seems now better. Let's see. Also at 6.5 because I have a and went out. You know, here we have a problem with tracking, but the system, it looks like we have problem with tracking. Yes, it doesn't reach. We see here because at 6.5 I'm applying an impulse, remember, then it will push it even, right? So let's repeat the movie. Alright, but it's stable, doesn't fail down. Okay, and this is evident here. So you can see how the system looks like. And this is theta. Alright, so it doesn't fail down. The system doesn't fail down. So those parameters are good enough for this system. Yes, of course, state space controller better for tracking. So tuning parameter is hard, like you have P, ID and N, 4 and 4, you have 8 parameters and they could be coupled together. So tuning 8 parameters that they affect each other is really hard, experimental. So that's why it's very important to have a model for your system. So knowing the model for your system, you can easily tune it, and having this a starting point in which you can implement them in your experimental system. Okay. I think for the system we have at the lab, also we have a model for it. So now I'll be opening it. So as you see, in crane control has to be inverted. So here you have plus and minus, plus and minus. Minus came from the angle. Okay, so we did exactly the same in our experiment. Because based on simulation, we found that's how it works, plus and minus. Yes, but in some other cases, plus and plus could work. So then you keep it plus and plus. So you add the control effort from the two controllers together. Okay, depends in the system actually. So in here, the overall system, x over x reference, for example, is not stable if it is, for example, plus plus or minus minus. But plus minus minus plus works. Okay. So you know, because PID it has problem with tracking. So usually, if you remember in here we used sine waves, so going this how. So then becomes easy. I mean, we don't really know how xref is following, not like a step. But if I'm using state space controller, for example, here, I may build better controller so I can even use step. Alright, and if you go to your session 9 here, so look, I'm here in session 9, previous session actually, and you look to the tracking, which is 1. So the system 1 to 3, then go back to 1, then after disturbance return back to 1. So then in our inverted pendulum at the lab experiment, we don't have even that distance, we don't have 3 meters. So then also step doesn't work unless if you have smaller step, like not 1, maybe say, okay, not 1 meter, maybe you say a little bit, but it works actually if you minimize, don't put 1 meter, or not necessarily, maybe put 0.5 meter or 0.3 or 25 meter, so then it works. So if 0.25 meter, it will overshoot 3 times more, so up to 0.75, so still acceptable, so still within the range of 1.5 meter, which is the length of the linear inverted pendulum. So you need to think. So then step is working good. You can do it if we are using state space controller, like in this experiment we did in lab 9. Okay, and want to say in session 9. Okay.